Greetings, Chem 110H. I'm here to flip the strong acid, strong base, weak base portion of the lecture. So let's go ahead and begin with a strong acid. And there are several classes of strong acids, and the first ones are the hydrohalic acids. And the halic part refers to the halide, so these are made out of something from the halogens, beginning with HCl, HBr, and HI, and the name is hydrohalic, so hydrochloric, hydrobromic, and hydroiodic acid. If you get stuck or can't remember how to name these, just think back to HCl, which everybody knows, hydrochloric, and name the other guys accordingly. If you take molecular hydrohalic acid and you were to bubble it into water, molecular means that it's still a molecule, there's still a bond, it's not ions yet. If you take this gas and bubble it into water, the bond instantly breaks, the bond between the H and the X, to create H plus dissolved aqueous hydronium ions, and then the anion, let's say chloride ion. And so these gases are extremely dangerous. You have to handle them with caution. You never want to get them into your eyes. They will dissolve and make a strong acid. And X here again is chloride, bromide, or iodide. It's not fluoride. So why not? Well, hydrofluoric acid is a weak acid. It's only about 1% dissociated into the ions. And the reason that HF prefers to stay molecular is that in this form it hydrogen bonds very strongly with water, right? We know that to hydrogen bond, the heteroatom here needs to be oxygen, nitrogen, or fluorine, and the best of all is fluorine. It's the most electronegative. So this H can donate to the oxygen on water, and this F can accept. It has three lone pairs, 1, 2, 3, not shown here, where it can accept from the protons on water. And those very strong hydrogen bonds are additional things that would have to break, interactions that would have to break in going to the right. And so that stabilizes this system. With that said, even though HF is a weak acid, it's very dangerous. Not all weak acids are dangerous. In fact, some of them we eat them and we enjoy them. Say acetic acid is in vinegar, and phosphoric acid is even in Coca-Cola. And so HF is very dangerous. It can etch glass, and the reason it's dangerous is it can penetrate our skin readily, and that's because it is mostly in this molecular form. The phospholipids on the membranes of our cells are negatively charged, and so they resist anions, and they have proton pumps that resist H+, but they don't resist HF. On top of that, here's another precipitation reaction for you that you should know, and that is that the calcium in our blood, remember it precipitating with oxalate and rhubarb, well, it will precipitate with F- to make calcium fluoride, which can lead to blood clots. So the second class of strong acids after hydrohalic acids is oxyacids. And these are acids which have HX, E for electrophilic, and then OY. And they're strong if the difference in the number between Y and X is either greater than or equal to 2. That makes it strong. And if it's less than or equal to 1, then the oxyacid is weak. And so here's an example of the application of that rule. We first look at per iodic acid, and it's important to review your nomenclature from earlier in the semester. It shows up here in the acids. And so now it's Y is 4 and X is 1, 4 and 1. And so when we subtract those, we get 3. 3 is greater than or equal to 2, so this is strong. Nitric acid obeys this rule, and the difference is 2, and we're all familiar with nitric acid being a strong acid. And a diprotic acid in its neutral form, such as sulfuric acid, is also strong, as we're familiar with. If we use the rule 4 minus 2, we get 2, and that's a strong acid. But this rule that I have up here only holds for neutrals. It does not work for anions. And so if we look then at the second deprotonation of sulfuric acid, and this is now of the bisulfate or hydrogen sulfate ion, this is actually a weak acid, even though Y minus X is 4 minus 1 is 3. And why is that? Well, as I said, it only holds for neutrals. Why does it only hold for neutrals? If you write down the dissociation here, you can see that the two products are going to be very strongly attracted to each other. It's now 2 minus attracted to 1 plus, whereas in all of these, it's 1 minus attracted to 1 plus. And this extra attraction drives the reaction back to the left. So just remember that this rule holds for neutrals, but not for the anions. In other words, if you have a polyprotic acid, it will hold for the first dissociation, but not for the subsequent dissociations. All right, so here's a few more examples that we worked for you here. And so these are all the oxyacids: perchloric acid, chloric, chlorous, and hypochlorous acid. And we can see that Y minus X goes from 3 to 2 to 1 to 0. The first two are strong. The first one is very strong. The second one is strong. And then we go to weak and very weak in hypochlorous acid. Here's another example of a polyprotic acid. Of course, this is phosphoric acid. And even though it has 4 oxygens, because it has 3 hydrogens, the difference is 1, and this is weak. And as I mentioned, phosphoric acid is a component of Coca-Cola. Which doesn't mean it's not dangerous. It will rot your teeth eventually, but in small amounts where our bodies are able to handle it. Okay, so why this rule that I gave you up here? Where does it come from? Well, let's contrast a very strong acid here in perchloric acid with a weak acid here in hypochlorous acid. And if you look and inspect both the formal charge and the oxidation state on the chlorine, and first off, this is the structure of the oxyacids. We know hydrogen's got to be on the outside. Hydrogen is sort of a capping molecule. It can only have one bond, so it must always be on the outside of a molecule. The most electropositive atom is in the center. We'll do more with this when we get to Lewis structures in a few weeks. And then the oxygens go around the outside. And when you calculate the formal charge or the oxidation state, either one, you can see it's highly positively charged. And so that positive charge on the chlorine kind of sucks in all these electrons and it weakens this bond. It makes it very weak, which means the H just comes right off of the molecule. If we go over here to hypochlorous acid, we can see the oxidation state and the formal charge are +1 and 0. Much less positive, much less electropositive. There's less of an inductive effect, and so the electrons in the oxygen also are also resonant here and interact with the H, which strengthens this bond. And so that makes this a very weak acid because this is mostly in the molecular form without the H being ionized. Let's move on to weak acids. The first class is carboxylic acids, and those are shown here. This is of this general form, R C double bond O OH. We'll also at times write this in the following way as RCO2H. And the carboxylic acids are described in the reading in the organic section. The additional chapters are now posted on the website, so be sure to look at those and be familiar with what a carboxylic acid is. And then over here we have the carboxylate anion and H+. Kind of the archetypical example on this is acetic acid, where R is a methyl group, and then this would be the acetate. It's a weak acid. Remember, weak acids have pKa's between about 2 and 6. This one happens to be 4.7. And note that the acidic proton here is this one, not the methyl group. And I also want to just write here that in the case of acetic acid, that there are other ways that we abbreviate acetic acid, at least in the molecular form. We abbreviate acetic acid as HOAC, and then sometimes we abbreviate it as HC2H3O2. So be familiar with both of those, and when you see it in equilibrium, the equilibrium lies mostly to the left, and so both of these would be written like this. Or here, the H plus in the same way, plus then the acetate anion being written and again, just please be cognizant of the fact that the acidic proton is this one, and that is the same one that you see over here, and that these three H's are not acidic because they're attached to a methyl group. We'll say more about that in just a second. Okay. So the second class of weak acid is hydrofluoric acid. We talked about that on the previous page. And then here's another example, hydrozoic acid. It's the protonated form of the azide anion. Azide is a poison. In fact, sometimes in the lab we'll add very small amounts of it to our buffers to keep bacteria from growing. And then the fourth class, also on the previous page, would be oxyacids, but where the y minus x value is less than or equal to 1. And then I thought it was worth just mentioning briefly about non-acids, returning just for a moment back to the idea of the methyl protons, or these are called methylene protons, or we can just have simple methane. These are incredibly non-acidic. The pKa on these are up around 50, meaning they'll never ever let go of their protons. In fact, if you ever were to make an anion, this would be exceptionally basic. So okay, on this page, I just want to go through the different bases, strong bases and weak bases. The strong bases are generators of hydroxide, and so they'll be soluble salts. You can consult your solubility table, and when you do, you'll see that the soluble salts are only are monocations, everything in group 1A, the alkali metals. You see them listed here. The ones we're most familiar with are lithium hydroxide, especially sodium hydroxide, potassium hydroxide. And of course, ammonium is also would fall into this class, +1, and being even more so because it has a very large radius. Then we move on to our weak bases. I've got 3 of them listed here. The first is related to the strong base, but it's not very soluble. It's only sparingly soluble. And so you might imagine if we start to charge up the cation, we'll attract the hydroxide more. And in fact, this is a problem with all metals to be familiar with. If you're working with a metal and the pH is 7, 8, 9, 10, something like that, you have to worry about the metal precipitating as a hydroxide. So people will often, if they want the metal to be soluble, will work in strong acids. And I'll do a demonstration for you in lecture, which is pretty nifty, showing you that magnesium hydroxide is a weak base, but with strong neutralizing power. And this is what milk of magnesia is. The second weak base are generators of hydroxide, but via hydrolysis. And the archetype here is ammonia gas. If you bubble that into water, as you know from the ammonia fountain demo, it dissolves. It's highly soluble through hydrogen bonding. And then when you give it water, it will lyse that bond in water right there to make ammonium and leave behind hydroxide. It breaks the bond heterolytically, but it only goes about 1%. Why? because it's really hard to break the bonds in water. They're exceptionally stable. Don't confuse that with ammonium hydroxide, where it comes in as a salt of hydroxide. This is a very strong base. This is a weak base. And then the last class of weak bases are your conjugates of weak acids. Remember, the conjugate of weak is also a weak. And so you know these because you know your weak acids. And so if HF is a weak acid, then fluoride is a weak base. If HNO2 is a weak oxyacid, nitrous acid is a weak acid, then the nitrite anion is a weak base, and azide is a weak base, and the carboxylates are weak bases, and then the oxy acids that are weak acids are weak bases. And just to show you why, I'm giving you one example. It's very similar to the one up here. If we put acetate in, it wants to go back and form acetic acid, but it has to lyse water, has to do hydrolysis, really hard to do. Reaction only goes a little bit. We generate just a little bit of hydroxide in these two examples, and this is a hydrolysis reaction. Thanks for listening.